Hold on, everyone. Just gotta get the chat open. All right. All right. Just getting right into it. Tonight we're going to talk about PIDs. The thing we use a lot on our robots. What's a PID? Mostly useful to remember what it's good for, which is a way to control something with analog output to a set point. You know, you can vary and break that down further. Analog output, like, you know, our motors, you know, they're not just on and off. You can give them like percentage powers. So, you know, it's a way to use math to like vary the output to get something to a set point, ideally smoothly. So a set point is just a place where you want the mechanism to go, usually represented in like math. So, you know, um, like, you know, you can represent like a lift, like how high you want it to go, or you could represent a like the drivetrain, how far forward you want it to go, or a flywheel, like how fast you want it to spin. Um, you know, any of those options, whether it's like, you know, set the flywheel to 3,000 RPM. 3,000 RPM is the set point. Set your lift to go up to 100 inches. 100 inches is the set point. It's where we want it to go. And then the PID uses some tuned constants and some math to, as it gets closer to the set point, to vary the output so that it slows down. So linear, so 2D set points are right out. Unless you have something else generating set points for the PID to handle another dimension, we'll go over that either next week or the week after. Well, no, probably next week because the week after is finals week. I still need to make the next lesson. A lot of these were generated months in advance, and that next lesson hasn't been made yet. What does it stand for? PID stands for proportional integral derivative, which are the three terms in the equation. Like, you know, you have like terms are separated by like a plus or a minus in an equation. So there's also another term called feed forward. So depending on what kind of PID we're doing, there's either 3 or 4 terms in the equation. You know, positional PID, velocity PID, just some examples. I'll actually pause here and do some, actually explain, which bargeman must have signed in. Hold on. And when is the school going to give me my own account? Wait, sorry, shared. Oh, actually, I was getting out of that anyway. Let me just bring up a Word document. So the equation for a PID looks about like, see if, so that's the first term, is the P constant, or the proportional constant, times error. Error is how far away from the set point you are. So actually, let me just choose a more reasonable size for this. P constant times error. And yes, PEMDAS means that these would be together anyway, but I'm going to put them in parentheses just to make it very clear how this is supposed to go. So that is the PID equation. Your set point, or so set point is like where you want to go. So like an example output of this equation, say P equals of course it goes back to the crazy large font I don't want to use. Example. Our tuned constants are so I guess go back to the equation really quick. I'm sure some of you are confused about the integral and the derivative of error. Actually, maybe for this first example, we're just going to set these constants to 0. Because if you want to ignore a term, you can set the constant to 0 and it will just cancel out whatever. You don't care what these functions return. So for this first example, we'll just do a simple proportional constant times error. So at some instant, set point equals 3000. Say this is for a flywheel. Speed equals, I don't know, 2000 RPM. So because the first, oh yeah. I'll also set feed forward because we don't care about feed forward in this example. So, you know, we can just get rid of all the rest of this for this example and just focus on the P constant times error. Just be P constant times error, or 0.5 times, and your error is just set point minus current. So if your set point is a speed and your current speed is 2000 RPM, it will be 0.5 times 3000 minus 2000, or 500, which our motors can't output 500, so or like, I think that's 5000% power that I'd be asking for. So in this example, this PID would, that we've kind of mocked out, would be trying to give it 5000% power, but we'll just get full power forward because, you know, we're 1000 RPM off of where we want to be. That makes sense. Now, if we change this so that it's, say, 2950 RPM, our error becomes 2950. That's 50 times 0.5. Our P constant in this example is terrible. Like, we would never actually have it that high. But, so 50 would be like 25. That's a bit crazy. So, for the sake of this example, let's try tuning this. So, setting it lower. And this is like actually how I would tune this a PID in this situation, is just look at what it would try to output in certain situations and say, is that reasonable? So 50 times 0.005. I probably should be able to do this without a calculator, but yes, 0.25. I should have been able to do that without a calculator, but in this case, 25% power is totally reasonable. So, you know. So yeah, that's kind of how the equation part of this works. Now back to this. So to be able to use a PID, you want a fast, low latency way to track the dimension the PID is operating on, whether it's rotational speed, distance, etc. Well, encoders are usually pretty fast unless there's some weird filtering delay like on the Spark Max. Potentiometers work pretty well. LiDAR. Oh, the potentiometers are analog ones. They tend to need some sensoring filtering, so that may make them a bit worse. LiDARs are fast. Sonar might work. A lot of times our PIDs are based on encoders. You need an ability to run the PID at very high speed. The faster it updates, the better in general. Um, at least 30 hertz. Spark Max runs at like 50. The Falcon 500 runs at 1,000. All our motor controllers can run the PID fast enough. To be able to use the PID, you probably need to have either watched this or some other lesson, or have some experience with PIDs, or, you know, want, you know, don't plan on using a PID unless you know how to use a PID. That doesn't mean you shouldn't investigate PIDs if you don't know, but, don't commit to it without being able to know it. For our team's purposes, I'm around and can help. So we definitely don't be afraid of using a PID. Known or discoverable set points. To be able to use a PID, you have to know where you want to go, or be able to figure it out, either through testing or whatever. You can't just say, robot, go over there. You have to be able to figure out, oh, it's this many turns of the wheel to get over there, etc., etc. Actually, I'm going to pause and be like, are there any questions so far? You have 1 minute to ask any question you want. Intermission 3D print because I'm printing an IO shield for a computer while waiting for questions. Oh, you might have to rewatch the VOD to catch up. That's why you need to be on time. Isn't that my IP? That's a local network IP. You can't do anything with that. If you go to 192.168.1.205, I have a firewall. You're not going to be able to connect to it. But also, I have a firewall, so, like, even if you had my public IP, there's not much you could do with it. Ah, yeah, it's fine. Like, that is the IP of my Octopi on my network. But anyway, back to Autumn Hud thinks that Graham said something inappropriate in Turkish. That's funny. Anyway, oh, so yeah, some stuff I already explained, but if you just got on, you might read through this really quick. PID equation. Hey, it's something I already explained because I realized at the last minute that it made more sense to go earlier to talk about the PID equation before, like, what it is before, like, what it takes to use it. Oh yeah, the feed forward is only used for velocity based PIDs. Simplifying a PID, if you set any of the constants to 0, that term in the equation takes no effect. So yeah, that derivative and integral thing that came up in the equation, calculus. Um, Derivative is the rate of change of something. In in our case, it's mostly just using the like concepts of calculus. You're not actually forced to do any calculus. You just need to have some understanding of the idea. So derivative is the rate of change of something. So like an instantaneous, like, how fast is this accelerating, or um how fast is the robot moving. Integral is the area under the curve of a graph. In this case, the computer keeps a running total of the error. Like, every loop that the PID loop runs, it just keeps like accumulating the error by just like adding it to a running total. Um, Also, there's a concept I forgot to explain. And I will Google it, or I will write it in a Word document because none of those. Wow, that's some nice graphical errors. So, how many of you have taken like a physics class? Like any kind of a physics class? This is really interesting. How far do I have to go before I get a, oh gosh. So I'm just gonna restart Word. So, uh, so here's a fun fact. Speed is the derivative of position. That is a very important concept. So, like, if you are driving in your car, if you are doing 75 mile an hour on 435 illegally, slightly illegally, your position, as in like your position as told by the mile markers on the side of the road, how fast that changes is the derivative, or how fast you like rack up the miles on the highway. Your speed is the derivative of that. And that's why it's like miles per hour. It is the rate of change of your position. Also, position is the integral of speed. So if you graph your speed in your car and you find the area under the curve, that will give you how far you went. Like, someone will prove it to you in some physics or math class. I'm sure if you take calculus, they'll do it. That we don't really have time to go through that example, but just remember these things. They are facts. You should, and they're useful facts. Um, Now, how to get the area under the curve or how to get the derivative of your position, you don't need to worry about that right now. There's a class that will teach you that when it becomes relevant. You just need to know that there are operations you can do. But you can, if you just like graph your speed like on a road trip, like every 2 minutes, it will give you like an estimation of it. The more often you like sample your speed to make the graph and find the area, the more accurate your estimate will get. And that's kind of what the robot code is doing. It's not doing the actual like derivative operation as you would do in calculus class. It's just sampling a sensor every so often, thousands of times per second. And the estimate it gets, because it's doing it, tens to hundreds to thousands of times a second, is really good. So that ends up being, I guess the getting a position by doing speed thousands of times per second is really good. The derivative, it's just looking at how far it's changed, but the position is changed between loops and getting the speed from that if it's going in that direction. Anyway, these can be taken forward. Acceleration is the derivative of speed. Like, and thus speed is the integral of acceleration. So yeah. So yeah, if you like do the derivative of an integral, it cancels out. If you do the integral of a derivative, it cancels out. These are like multiplication and derivative, and multiplication and division in that sense, kind of. Or maybe more like addition and subtraction. I think you get the idea. Yeah, I probably didn't do the best describing that, but we'll move on. Oh yeah. Integrals are forever. They accumulate forever unless you reset the accumulator. On our motor controllers, there's the concept of an I zone where it doesn't start accumulating integral until you get kind of close to the set point. there's a reason for that will make more sense. So finding your constants. There's a link to a Wikipedia article. Um, that kind of just says the manual tuning method. That's usually what we go for. So if you guys have, the WPI lib on your computer, and you go and clone this repository in GitHub, you will get this. And if you simulate it on desktop, it fails because I have the new version. Why is it? Let's try 2021 VS Code for this. Wait, why is this building our actual robot code? Told it to open something completely different. And if I open the driver station, so if you're running this code and you open the driver station, you have these buttons. You edit, so you can edit these. And so if I do like a set point of 500, or maybe I have to enable. So if I do move to top and go over to the live window, see elevator velocity, elevator position, and the set point. You can do the shuffleboard is drag this over, right click, show as graph. And if I go to the bottom just to give scale, also gonna take the set point and show it as a graph. You can see that this untuned PID, like it gets it close to the set point because we're, set point is 2.0. Here's 2.0 here. But it oscillates around it a lot. Like you don't want the robot, moving up and down or anything on the robot oscillating like that. That's really hard on mechanisms, various things, etc. And that like sharp hit down would like really hurt most robots actually, because like it's like stopping it right there. I'm going to get rid of this stuff that does nothing for us. So over in constants.java, there's this KP, KI, and KD. You are free to use this project and mess with them to try to tune the PID to make it as smooth as possible. You can either use the Wikipedia method, you can just play around with them. But the idea is to eventually, by like this time next week, or at least sometime before the actual season, get this PID running like actually nice. For example, I make the PID like 0.1 and save it. Stop the debugger. Emulate robot code on desktop. Compiles. Didn't. There we go. All that. If I enable, and then go to elevator mid. Go to elevator mid. Okay, if I actually enable and then go to elevator mid, that works way too well. Well, oh wait, that's the set point. Oh, the actual lift just isn't even moving. So yeah, having your p value too small just means like it either doesn't move or like this. Let me make sure that's saved. Oh. Yeah, you have to stop it before you can run the sim again. Check these and hit OK. So yeah, 4 is like still way too high. So if I remember the Wikipedia method well enough, increase KP until the loop oscillates. That means you want it to like the lowest value where it's like oscillating. So I will tune the P value first, then I'll leave you guys on your own to go do the rest of that method with this. Idiot and didn't stop the simulator before trying to build this again. So yeah, that's that half. That still really oscillated, but it actually kind of stopped after a while. Let's see what happens when it goes up. Yeah, disable that. And then let's just try a KP of like 1. Being really annoying right now. Let me see if I can find a task that needs to be ended. Wow, shuffleboard is using a lot of my CPU. Okay, so I'm going to teach you all something here. Go to Task Manager, Performance, and Resource Monitor. So if you're ever having trouble where you're trying to like write to a file because some process that you don't know about is using it, what you can do is you can copy the path. You can copy the path. Hope that worked. And then in Resource Monitor under the CPU tab, there's associated handles. You can actually search for that handle, and it'll take a minute. But a lot of times this beats like restarting your computer to kill a task that you don't know what it is. Um, search results for. Maybe it's good to go now? No. Maybe it's using this file? Maybe this error message just stinks. Doesn't actually say what's wrong in a easy to understand manner. Weird. If it's in use, I would expect something to actually be using it. I swear I do this all the time and it works for various things at work. Hmm. Well, if you have a suspected service, you can see what all this is using. Isn't that? Fire station using it? Huh. I don't know. I guess I'll restart VS Code. All right, it was just VS Code being dumb. I mean, actually, Gradle being dumb, but so now with a KP of 1 finally, I would say 1 is where it's just starting to oscillate, really. So you all are free to do this yourselves and try to get it tuned really well using PID in that method. Let me go back to this and see if there's anything else. Oh yeah. So why is that elevator PID not why does it not have a feed forward? Uh, so a feed forward is a term in the PID equation that is just your set point times a constant. It's designed to give the motor enough power to hold the set point. I guess in theory you could. Well, I have taught it as for velocity only. I guess on a lift, if for some reason it gets heavier as you. No, that doesn't make any sense. You would never do a feed forward like that. Yeah. So yeah, feed forward is for velocity only. So why did the elevator PID not have a feed forward? It's positional. That is correct. Because we're not controlling, we're not, the set point of the elevator isn't a velocity. We're not just saying go up at 20 inches per second, because then it would just, when do you stop it? Do you stop it when it goes so high that it stalls the motor out and breaks things? That just wouldn't make sense. So elevator PIDs are usually positional. The hood PID on our 2020 robot is positional. And so there is no feed forward. So yeah, how to feed forward. Set the value so that when error is 0, the set point times the constant KFF, feed forward constant, gives the motor enough power to keep its speed. So it's useful on things like the flywheel, or for reasons. There are times when we give the drivetrain a velocity PID, and so that has a feed forward. But anyway, I think that is it for this lesson. Um, yeah, for those who came in late, watch the VOD. If anyone has any questions, I'll stick around for a minute or two, and then we can call it a week. Well, you guys still have this stuff to do, but and Gavin. Also, if you watch the VOD and you still have questions, we have Slack, we have GroupMe. Do not be afraid to ask. '3D print still going. Well, if no one has any questions, well, other than me questioning why there's just garbage in my throat, uh, either I did a really good job of explaining, or I expect some questions later. Anyway, have a good rest of your week. Keep working on this stuff or this, and see you next Wednesday.